Okay, today we're going to start a new chapter called Hahn-Banach theorem. Okay, so the theorem itself it's about the extension of a linear functional from a sublinear space, a linear subspace to the whole space. So it has many applications. So in a linear functional analysis, so we're going to first consider the setting like this. So we have a Banach space X, and then we have X naught, which is a linear subspace of X. So this is a linear subspace. And we have a linear functional on this X naught. So let's call it F naught. We consider real case, but there is also a complex version of this, but we'll only talk about the real Hahn-Banach theorem here. So the F, is from X naught to R, or in other words, it's linear, bounded linear functional. So actually we mean this. Okay, it's in the it's a linear, continuous linear functional defined on X naught. And besides, in addition to this, we also have a sublinear function that is defined on the whole space X. Recall the sublinear function is that when we have two vectors x and y, this only have this. Right? Only have this thing. That's a sublinear function. So this is linear. F naught is linear, but this is sublinear. And we also know that the F naught is bounded above by this P. That means for every x in X naught, we have this, okay, over the linear subspace. Now the question is, can we extend this X naught to the whole space? So can we extend X naught from, originally it is defined on the linear subspace X naught, but we want to extend it to the whole space X, such that, so when we extend this F naught to the whole space, we call the extension F. So that means to get this F that is it's a linear functional on the whole space, such that when we restrict this F to the linear subspace, it is the same as the F naught. And also, this extended function F is also bounded by this P on the whole space. In other words, F of X is less than or equal to F of P of X for any X in the whole space. So here it is only on the subspace because the F naught is only defined on the linear subspace. But we want to extend it to F, which is for the whole space. Okay, so that's the question. And the answer to this question is yes. And that is exactly what the Hahn-Banach theorem says. Okay, so let's state the theorem and then prove it. Okay, so as we said, with this X be a real linear space, and the X P is a sublinear functional. Okay, and the X naught be a linear subspace of X, and this F naught is it's a continuous linear functional. Okay, actually we can even make this slightly more general. Just let X naught be a linear functional on x naught such that f naught of x is less than or equal to p of x for any x in the linear subspace. Okay. Then the conclusion is there exists a linear functional, not necessarily unique, but there exists a linear functional f is from x to r such that first this f of x is again bounded by this p. And the second one is that if we restrict f to the linear subspace x naught, it is equal to the f naught. Okay? Or in other words, f of x is equal to f naught of x for all the x in the linear subspace. Okay? That's the Hahn-Banach theorem. Okay, let's see how to prove this. So the idea is we have this x naught as a linear subspace, then we consider a simple extension of this, just by extending it a little bit and see what happens, and then continue doing so to eventually extend to the whole space. Okay? So the first step is to see what's gonna happen when this x0 or x naught is extended a little bit. We first consider a simple extension of that. Say consider x naught or y naught to be in x minus x naught. X and x naught are different. If they are same, then we don't need to do anything, right? So what is interesting is that x naught is a proper linear subspace of the x. So in this case, there will be some element that is in x, but not in x naught. So let's say we have this y naught that satisfies this. Then consider a slight extension of the x naught. We call it x1. So x1 is defined as follows: is x plus a times y naught, where this x is from the linear subspace x naught, and the y is the y naught is the one, which is the set, and the a is any real number. Okay, and this x1, and it is easy to show that this x1 is a linear subspace of x. Okay, it's again linear subspace of x, but it contains the original x naught, since when you set a equals to 0, then it's just you just get all the elements in the original x naught. Okay, so this is the extension of the x naught, but it's still a linear subspace of x. Okay, and then suppose we have an extension from x naught to this x1 such that the extended function satisfies these two conditions. Then suppose this is a linear functional that satisfies one and two. Okay, now let's say we're only concerned about the property of f on this x1, and then you can see that according to the definition of x1, every element in the x1 can be written as x plus a y naught, right? But because f is a linear functional, so we should have f of x plus a f of y naught. This is true for any x in the subspace x naught. Okay, this should be true for any x and for any a. Okay, so now we take we take specific values of y naught, or specific values of x and a. Say we take a to be -1 and x to be some z, but z can be, sorry, negative z. Negative z can be any number in the x, any vector in x naught. So let's see what happens. We will have f of, let me write it in the middle, f of, so now x is negative z, right? A is 1, so I have y0 minus z. And because it's linear, I know this is the f of y naught minus f of z. But on the other hand, because this f should be bounded above by this sublinear functional p, so I know that this should be less than or equal to p of y naught minus z. Okay, I should have this. And similarly, then we take a equals to 1. And then I take this x to be arbitrary y in y naught, in x naught. Then what happens is, remember that same as before, this is just 1, this is the y. Then we'll have y naught plus y, which due to linearity of f, I should have f of y naught plus f of y. But on the other hand, I know that this should be bounded above by p of y naught minus y. Okay, so now I have two equations or inequalities, say star and double star. Okay, so as you can see that right now we need to determine, see, if I want to determine what this f is, I only need to determine what this one is, because f should be the same as f naught on this space. So this one here is essentially just f naught. Okay, this should be just essentially f naught. And the only thing that is undetermined is this part, right? If I want to determine what this f is defined over this x1, I just need to determine what this one is. That means I only need to know the value of f on this single point, y naught. And now it tells us what is the y naught is. The y naught here should be subtract the f of z should be less than or equal to this for any z in the x naught. And remember that here, this f z, since z is in x naught, this f should be just f naught. It takes the same value as f naught as z. And similarly, I have this one here, right? And now this tells us some constraint or condition that f of y naught should satisfy. So one is this, the other one is this. So I need to know that I need to make sure that f of y naught should be less than or equal to this plus that. And at the same time, I need to make sure that this f of y naught should be less than or equal to this. I'm sorry, should be this. This should be. So when the a is -1, I should have let me see, it should be this. I'm sorry, I mess up here. So I should take a 1, a -1 here, a -1 here. Let me rephrase this. So I take a to be 1 and this x to be -z. Then what happens is -z plus y naught. This should be equal to negative f(z), which is just f naught of fz, because the z is from x naught and f is equal to f naught on the x naught. And this is f of y naught. And on the other hand, I should have this less than or equal to y naught minus z, which is switched. I just rearrange it, right? And then I have here is -1, x is equal to y. So here I will have y naught. Sorry, y naught, and this is y minus y naught. And here I should have y minus y naught. And here on the right hand side, I should have f of y minus f of y naught. But the y is from the space x naught, so this is just f naught. So now you can see from the star, I know that f of y naught should be less than equal to p of y naught minus z plus f of z. This is because of star. On the other hand, I should say that this f of y naught should be greater than or equal to f of y, f naught of y minus p of y minus y naught. Okay, and this one is due to x double star. This should be true for any y and any x. Sorry, any y and any z from x naught. Okay, so my y or f of y naught only needs to satisfy this. Or in other words, I want to show that f of y naught is between the infimum of p y naught minus z plus f of z, where z is from x naught. On the other hand, I need to make sure that f of y naught is bigger than or equal to the supremum of this minus p of y minus y naught, where again y is from x naught. So I need to make sure this is true. Okay, so the only question right now is if this one is smaller than or equal to this one, so that I can leave some space in between. Otherwise, this will not be possible. This is the only condition that f of y naught we need to satisfy. So we just check that if this is true. Okay, to check that if it's true, essentially we just need to check that if this is always less than or equal to this for any y and z. Okay, so to show that, let's see, we are going to so we're going to move this to the left. Okay, so we need to check or need to show f naught of y minus f of z. This is what happens when I move the f naught of z to the left. And also I will move the p's to the right. I only need to check that this is true. Show that this is true for any x naught, y, z, and x naught. And actually it is true. The reason is because this, since the f naught is linear, I know that this is a f naught of y minus z. Okay, for any y and z, this should be true. On the other hand, this should be less than or equal to p of y minus z, because the f naught is bounded above by p. And this p, if I do a slight change, instead I just subtract the y naught and add it back, I'll have that. And now I have this part and this part. Remember that the p is sublinear, so the p of the sum of these two should be less than or equal to the p of this plus the p of this. And that is exactly this one here. That's why I know that this is going to be less than or equal to that. So this is indeed true for any y and z. Okay, so that means this is at least possible, right? This is possible. And remember, this is the only requirement we need for f of y naught. So as long as f of y naught is in between, then this f is a valid extension of f naught to the x1 space. Okay. So we show that the Hahn-Banach theorem is possible, or is true, when we just do a simple extension. And one remark here is that this choice of fy naught may not be unique, because maybe this is strictly smaller than this, then you have even many choices in between. Okay, but that's for the simple extension. Now let's consider extending this to the whole space. Okay, so to do this, let's consider the family of extensions of x naught. So I'm going to denote this f to be the extension of the f naught. So what we mean by that is this family f contains the pairs like this where X delta is a linear subspace contained in X, but also it contains the X naught. Okay, and also this F delta is a linear functional on X delta, and also it is an extension of the F naught in the sense that when you restrict the F delta to X naught, you just get the original F naught. Okay, so this F naught, this F delta is a linear functional here. Okay, so that's the family F I'm considering. Okay, given this function, given this set F, I can define an order. We say that define an order, or partial order, I should say, because not all the pair, not every pair of such things can be compared. Okay, so we say that X delta 1, F delta 1 is less than X delta 2, F delta 2 if the X delta 1 is a linear subspace of X delta 2, and the F of delta 2 will be restricted to X delta 1. This is the F of delta 1. So that means if this contains this space, and the F of X2 is the extension of this to the larger space, then we can define this order. Okay? And apparently not every pair, not you pick up any one and any other one of this, not necessarily they can be compared, but we can still define this order here. Okay, so this is kind of partial order, and we can now think about a and this F is a partially ordered set. Ordered set. Now we consider the totally ordered subset. So let M be a totally ordered subset of F. So what that means is this M contains a sequence of such pairs we call the X delta K and F delta K. Such that X delta 1, F delta 1 is less than X delta 2, F delta 2, less than the C order. Okay, so this is a totally ordered subset. Okay, so one is smaller than the other. Okay. And then we can show that there is a upper bound for this M, which we denote this by, say, xm. We denote it by the union of x. K is from 1 to infinity. And also we can define this F, which is a mapping from, or xm, is a mapping from xm to R, such that the F of M will be restricted to X delta K. It is just the F of delta K. Okay. So what this one is, it's just taking the union of this linear, because we know this is next to the next one, so on and so forth. So we take the union of them is still linear subspace, which we could denote by xm. And also we define the linear function fm on this linear subspace, and it just coincides with each one of them because every one of them is just extension of the previous one. So we can still define this f that is the same as each individual one. We restrict to the specific linear subspace. So that is an upper bound. So apparently this xm, fm, is an element in F. So, and also this is extension, or it's just covers, or it contains every pair in M. So that means, so xm, fm is an upper bound on of F. Okay, so we know this is true. And then, if since every element, every totally ordered subset M, we can show that there is an upper bound. And by the Zorn's lemma, we know that there exists a maximum element in F. There exists a maximum element we call the x lambda, f lambda, which is maximal of F. Okay, that means for any element in F, it must be less than or equal to this one, to this x lambda, f lambda. Okay, now we claim that x lambda is equal to x. Okay? Because if not, then there exists some, say, y naught that is in x, but it's not in x lambda. Then we can do the same procedure as in step 1, just to extend this x lambda to this x lambda, maybe called prime, which is just x plus y, a y naught, where this x is from x lambda, a is from any real number, and then we can extend this f lambda or this x lambda to a larger space, which is this, and we're also going to define this f lambda prime, that is an extension of this f lambda. Okay. Then this, then we can extend x lambda, f lambda to x lambda prime, maybe f lambda prime. Okay, and this is a proper subset of this, since it contains something, the letter contains something that is not in this. But this is a contradiction to this x lambda being maximal. Right? That's a contradiction. Which contradicts to x lambda being maximum. So that's why the assumption cannot be true. We must have this. Okay? And that completes the proof. We just keep extending this and consider all the possible extensions. Then this is a partially ordered set. Then we show that there is a maximum element of this partially ordered set, and we show that the maximum element is actually the original F. Is the entire space X, and this F, corresponding F, is the extension of the F to the whole space. Okay, sorry, I should say that this F delta is also bounded by P. Okay, so that's the whole space F. Okay, let's see. Oh, it's bounded by P, but it's only because F delta is only defined on X delta. So when we restrict P to X delta, it can bound this F delta. But otherwise, the proof is completed. Okay, so that's the Hahn-Banach theorem. We're going to talk about several corollaries and its applications. And then the next section, we're going to talk about a different point of view of Hahn-Banach theorem and see where the application of that is. Okay, so we first consider a corollary, which is as follows. Suppose we have a B star space. Okay, and then we have a linear subspace of X. Okay. We also have F naught, which is a bounded linear function of this linear subspace. Then there exists some F that is a bounded linear functional on the whole space, such that first, the F of when we restrict it to the X naught, it should be coincide with the original F naught. Okay. Secondly, this F should have the same norm as the F naught. This X naught, this norm, is the norm on this linear subspace. Oh, sorry, it's defined on X naught star, right? Which is the space of bounded linear functionals on X naught. Okay, because this is the only thing we can use to define F naught, since F naught is in here. So we can only consider the norm over here. Okay, so that's the corollary. This is going to be, I'm going to use the Hahn-Banach theorem to show this. Well, the key is that what is missing, comparing this one from the original Hahn-Banach theorem, is the sublinear functional, right? So this part should be straightforward. It's that we are looking for extension, but we're looking for extension. It should be bounded by some sublinear functional. And the other thing is to show that the norm actually is retained, is kept. Okay. So how are we going to define this sublinear functional? I'm going to define it as, for any x in the space x, in the whole space x, we define the px to be this times the norm of x for any x in the whole space. Remember that this is just a constant, so I can still define this x over the whole space because it's just that. And then apparently you can see that this is a sublinear functional, right? Because this is just a constant times the norm, and the norm is a sublinear functional. Okay, another thing is, as you can see, the F naught of x, you look at this, it should be less than or equal to the F naught in the x, which is equal to P of x for any x in the linear subspace. Okay, so the F naught is indeed bounded above by this P. So by Hahn-Banach theorem, we know that there exists F, which is a linear functional, continuously is a linear functional here. I should say I should first say this. It's a linear. We haven't shown that it's continuous or bounded yet, but we know that it's a linear functional such that the F of x naught, F when restricted to x naught, it should be equal to f naught. Right? That's one thing that the Hahn-Banach theorem tells us. And also, the f of x should be bounded about by p of x, and this is equal to this constant times the norm of x. And this is true for any x. Okay, so you have that, we have that. And if this is true, apparently we take a negative x, it will be the same, right? We'll show this less than or equal to this, again, the norm of that, because negative x has the same norm as x. So combining these two together, we actually have f of x bounded about by f naught of this. And this tells us that f actually is bounded, and that implies f is linear. So f is indeed in x star. Okay, and not only that, we show that the norm of f, according to what I have here, it should be less than or equal to this. Okay, but we actually want it to be equality. I want this to be equal. So we want to show that this is also true. And how do we show that? Recall the f naught norm, which is in the x naught star space. By definition, is just the f naught of x divided by x, where x is from the x naught space, but it's not 0, right? That's our definition. And because on this space, for every x in this space, the f should be the same as f naught, right? We know this. So that means the numerator here is just the f itself. It should be divided by the norm of x. This is x in x naught minus 0. Okay? And from here, we know that this is equal to, it should be less than or equal to the supremum. Now we have f defined on the whole space. If you were able to take the supremum over the whole space x instead of this x naught, then we probably can get a better supremum, right? Better value or larger value. So that's why this is less than that. Okay? Just because we're taking the supremum over a larger space. At the right hand side here is the definition of f. So that's why we showed the other direction, is that this is less than or equal to this. So we have this. Therefore, the f norm should be equal to the f naught, the norm of f naught in this x naught star space. Okay, and that completes the proof. We showed that this f is a linear function over the whole space, such that when we restrict it to the x naught, it's the same as f naught, and the norm of f is kept the same as the norm of f naught in the smaller space. Okay, that's the corollary. Okay, so that finished the proof. Another corollary is this. From the Hahn-Banach theorem, it tells us that for any two different elements or vectors in the space X, there exists a linear functional to distinguish them. What we mean by that is for any x1, x2 in the space X, where these two are different, then there exists some f as in x stars such that f of x1 is different from f of x2. Okay, so there's always a way, always a linear functional to distinguish the two different vectors x1, x2. Right? There's always a way to distinguish them using the linear functional. Okay, let's see the proof. Because x1 and x2 are different, so their difference should be non-zero. Let's say it's x naught. It's the difference between them, and that is non-zero. Okay, and then we consider a linear subspace x naught to be just a span of this x naught. So the A is just some real number, and this is a linear span of that. Okay? Then we define this f from x naught to R by f of x. So now remember that we have every element in x naught can be written as in this way. So we just define this to be f naught. Okay, we define this to be A times x, the norm of x naught. Okay, now I'm going to show that this f naught is linear in the space x naught. Because we can show that f naught is linear. Actually, not just linear, we want to show that is let's first show that it's linear. Okay, to show it's linear, we just need to show that any linear combination of two elements in this space x naught is, let's say the f naught, any two elements. So one element I called a x naught, the other element I called a prime x naught. Okay, and any linear combination of these two will be still, it satisfies the linearity. So let's say that the first one is using C1 as a coefficient, the second one is using this as a coefficient. Okay, now you can see that this, on the one hand, it is equal to f of C1a plus C2a prime times x naught. And according to the definition of, f naught, according to the definition of f naught, when it is applied to some constant times x naught, you will just get the constant times the norm of x naught. So that's just equal to C1a plus C2a prime times the norm of x naught. And now I can split them. This is just the C1 of a x naught norm plus C2 of a prime x naught norm. But remember that this, by definition, is f naught of ax naught. This is the f naught of a prime x naught. And remember, these two are some points in the space x naught. Okay, so that shows that this f naught is actually linear in the space x naught. Okay, so that's pretty easy to show. And from here, we can also show that the f naught of ax naught, the norm of this is equal to the norm. On the right hand side, I have the absolute value of this, right? And this is just the a times this. Okay, and according to the definition, because the norm is homogeneous, so I know that's just a x naught. Okay, so when we apply f naught to any element a x naught in the space x naught, I know that is less than or equal to this, or is equal to this. Okay, and this implies that this is indeed a linear function, is indeed a bounded linear functional whose norm is just equal to 1. Okay, and then by the previous corollary, now I have, remember that now I have x naught, which is a linear subspace of x, and I also have x naught that is defined, it's a bounded linear functional defined on x naught star. So by the previous corollary, we know there exists some f, which is in x star, such that the f, when we restrict to x naught, is just equal to f naught. And also, when we look at the norm of f, it is equal to the norm of f naught, which is equal to 1. Okay, we know this. Well, we know this is true, so when we restrict this to this x naught, when we restrict to f to x naught, we'll have, say, for example, let's pick up x naught, which is the element. This is the element in x naught, right? And I know that this is equal to f of x1 minus x2, since this is this definition for the x naught. It's just a difference of the two vectors. And because f is linear, I know this is just f of x1 minus f of x2. Okay. And also, on the other hand, I know that when we restrict the f to this space, this should be just equal to the f naught of x naught. But by definition of this is just equal to the norm of the two, of the x naught. But this is non-zero, since x naught is non-zero, so this is non-zero, and that means this is non-zero, right? And this means that f of x1 should be different from f of x2. And this is how we get this linear functional f, right? It's a linear functional f that takes different values at these 2 points. So we found some linear functional f that can distinguish these two numbers, or these two vectors. Okay? That completes the proof. Okay. Okay. And there is also another corollary, which is really simple to show. That I will skip the proof. You can do it, try it yourself. Suppose we have a B star space. Okay, and we have, say, for any x in so x naught is a linear, right here. X naught is a linear subspace of x. Okay, and let's say for any x in this, there exists f star such that f will be 0 when we restrict it to x naught. No, I should say this. Just do need to this. Do need this. Then for any x in x, there exists, sorry, it's non-zero. There exists some f x star such that the f of x naught, sorry, f of x naught is equal to the norm of x naught, and the norm of f is equal to 1. So this is just a very, we actually can see this from the proof above. This x naught is essentially just the same x naught as the previous corollary, just x1 minus x2, right? And then we show that there exists some f in continuous linear functional f such that it's taking this value, because this is essentially just a f naught. Sorry, this is just the f of x naught, f0 of x naught. On the other hand, we know this f naught has the norm 1, and this is how we extend it, right? So this is just the proof is actually a subset of the proof above. Right? So what this corollary tells us also is that if you have some x naught, if you have some x0 which is non-zero, then you must be able to find some linear functional such that f of x naught is non-zero. In this particular case, is equal to the norm of x naught, which is different from 0. Okay, or in other words, some element, if you want to show some x is equal to 0, you just need to show that f of x naught, f of x is equal to 0 for any x, sorry, for any f, linear functional f. Okay, so that's the remark I want to make for the from the for the corollary. Okay. Now let's consider another result or corollary from the Hahn-Banach theorem. So remember that we have a B star space. Suppose we have a B star space X, and we also have a linear functional, continuous linear functional defined on X. Okay, and now we say we have the null space of this F, I denoted by M, just the elements in X such that Fx is equal to 0. So this is clearly this is the linear subspace of the whole space X. Then we define the distance. So for any x naught, say in the space X, define the distance between x naught and M. We know that this is by definition the infimum of the norm of the difference x naught and x, where x is from this linear subspace. Define that. Then what do we know from here is that we can find a sequence in the space M such that they converge the distance between, so the sequence sk, we can show that this is going to converge to the distance. Right? This is something we know before. Okay. But what I'm going to say here is that, say, we choose this sequence xk just to show it more clearly. We choose this sequence xk such that the distance between x naught and xk is going to be less than or equal to, let's say, the distance between x naught and M plus 1 over k, right? This is because this distance chosen as the infimum. So I know that I can have a sequence xk that satisfies this for k, for any k, integer k, or natural number k. Okay. And now you look at the f of x naught. So I know that this is equal to this because xk is in the null space of f, is in the space M. So this is essentially just 0. Right? So I subtract it, it doesn't matter. But because f is linear, I know this is true. Okay? But on the other hand, because f is a continuous linear functional, so it's bounded by the norm of f times the norm of x0 minus xk. And because of this property that I set for the sequence, I know this is going to be less than or equal to the f times the distance between x naught and M plus 1 over k for any k. But remember that this is true. This is less than this for every k. So when k goes to infinity, I will have the f of x naught is bounded about by this times the dx naught M. Okay, it will be bounded by that. Okay. So the question right now is, can we find, suppose that we just have a linear subspace M. This M is not necessarily the null space of something, it's just some linear subspace of X. Can we do the reverse? Let's say, can we find some linear functional f such that the f takes the value over the whole space M, whole linear subspace M, and at the same time, the for any given x naught, so question is like this. If there as X is again B star space, the M is a linear subspace of X, and we also have some X naught that is in X but not in M. Question is, if there exists some F in X star such that the F is completely 0 on M, and the F of X naught is equal to the norm of F times the distance between X naught and F. M. That's our question. Okay? The answer to this question is yes, and that is going to be proved by the following theorem. Okay, so theorem is just what we're trying to say. The X is a B star space. Okay, M is a linear subspace. Okay, and X naught is in X but not in M. Okay, actually, we're going to define the delta to be the distance. We denote delta to be the distance between X naught and this M, which is positive. Then there exists some F in X star such that F, when we restrict to M, is just 0. And also F of X naught is equal to the distance, and also df takes the norm 1. Okay, in this case, you can see this will be just 1, this will be delta. Okay, f of X naught is just equal to delta. Okay, that's the claim we can make. Okay, let's see how to prove this. Okay, to prove this, let's think about the following linear subspace, X naught. This X naught is the, I should say, all the elements that look like this, X prime plus A X naught, where this X prime is from the M, and the A is from R. Okay, and X naught is the, as given in the theorem. And we're going to define the F as a mapping from X naught to R by, say I have some element, X prime plus A X naught. I'm just going to define this, because any element in the X naught space can be written in this way. I'm going to define this to be the A times delta. Okay, I'm going to define in this way. Then we can show that this is a linear. Functional, because again, let's see, we have two. Suppose we have two elements from there. One is called x1 prime plus a1 x naught. The other one is called x2 prime plus a2 x naught. Okay, and then when I make a linear combination of the two, say c1, c2 of the two, I want to show that f. And when I apply this to, let me use the f naught here because it's only defined on a smaller space. I want to show that this is just the c1 times f naught of the first point, and plus c2 times f naught applied to the second point. Okay, and if you can show this, then they will be linear. The f naught should be linear. Okay, since that's not easy to and that's not difficult to show, you just combine the c1 x1 prime plus c2 x2 prime, and then you have the c1 a1 plus c2 a2 together times x naught. Right, that's what happens inside. And because of the definition of f naught, this part is just in M. Okay, and this will be just equal to C1 A1 plus C2 A2 times delta. And apparently this is equal to the C1 A1 delta plus C2 A2 delta. And you can show that this part is just equal to this. And this part is equal to this. And that shows that this f naught is actually linear. Okay? It's a linear functional. Okay, and from here, we can also show that it's a bounded linear functional operator because let's look at this bound. So the f, look at this, x prime plus a x0. We know that this is equal to a delta. Okay. Okay, and so I should say this should be this. And that is this is equal to a times the distance between x naught and m. And if I pick up a specific point from m, say this point is going to be x prime over a plus x naught. So apparently this is from m as well. Sorry, this is from x naught as well. The reason is this is in m, okay, or negative of this, I should say in this way. Let's look at this value, dx prime over a and plus x naught. So apparently the x naught, this is equal to x naught minus x prime over a, and this part is from m, right? So this distance must be bigger than or equal to this distance here, since this is infimum of that distance, right? So that's why this is going to be less than equal to a times the norm of x naught minus negative x prime over a. And this is just the same as a times, just change it back to that, it's not. And from here I can put this a inside because the norm is homogeneous. So I have x prime plus a x naught. Okay, so from here you can see, sorry, I should have the f naught here. From here you can see that the f naught over this x naught space should be bounded by 1. Okay, and this implies that f naught is actually a linear functional over here. Okay, and then by the previous corollary, we know that I think the first corollary after the Hahn-Banach theorem, there exists f in x star such that f takes the same value as f naught, and the norm of f is equal to the norm of f naught, which is equal to 1. Okay, but recall what we're trying to prove. We did prove this right now, and we just need to verify these two. Okay, just verify this and this. Okay, so the good thing is that both of these two cases fall into the x naught space. So we know that if x prime is from M, then the f of x prime is equal to f naught of x prime. Okay, but by our definition is x naught, x prime plus 0 times x naught. So this will be definitely 0 times delta, which is 0. So for any x prime in the space M, we know that f of x prime is equal to 0. And also, when we look at f of x naught, this is like 0 plus 1 times x naught. So this is why because this is equal to f naught of x naught, and that is by definition is equal to delta. So that's how we verified these two. Okay, so now we have all the three verified. That completes the proof. Okay. So let's look at the last corollary. Suppose we have a B star space with a norm, and we have a subset. M is a subset of X, not necessarily subspace, just subset. So we can take the span later on. And we also have some x naught, which is in the space X, which is non-zero. Okay, and then we can claim that the x naught is in the span of M closure. So we take the span first and then take the closure of that. If this x naught is in the closure of the span of M, if and only if the f of x naught, so I should say only if that when f is in x star, and also f when we restrict to M equals to 0 implies the f of x naught is 0. Okay, so the statement of this is equivalent to the statement here. Okay, so let's show from the left to the right. Suppose we have x naught in the span. And then let's say that we have some f that is a bounded linear functional on x, and the f is taking 0 over the M. Then, because x naught is in the span of the closure of the span, so we know that should say that closure of the span, we know that there exists a sequence xk which are in the span of M, such that xk converges to x naught. Okay, and now suppose we have this f. If f is in x star, and when we restrict f to M is 0, then f of xk should be 0, because xk is a linear span of elements in M, but f takes the 0 value over M. So, and also f is linear. Remember that xk can be written as something like a1 y1 plus all the way to an yn, or yi's from the M. Right? This is how we say the xk is linear in the span of M. But if we apply f to xk, then we'll have a1 f of y1, so on and so forth. But each of this is 0. So that's why we must have 0. Okay? We'll have this equal to 0. So that's what we have on the one hand. But on the other hand, since f is continuous functional, so the f of xk should converge to f of x naught, because xk converges to x naught. And we just have a sequence of zeros that convert to f of x naught. That means this must be equal to 0. Right? That shows this direction. The other direction, suppose we have this property, then we want to show that x naught is in the span. Okay? So if not, then that means there exists some, I should say, if x0 is not in the closure of the span, then by the previous corollary above, we know that there exists some f in x star such that when we restrict f to m, we get 0. Okay, and also the f of x naught will be equal to, or f of x naught is equal to the distance between x naught and m. This m is the, so this m is the closure, so I should say, not just this m. We have this, which is greater than 0. Okay, so but if this is the case, we will have violated this condition right here, because we do have some f of x star that takes the 0 over the space M, but f of x naught is some number that is positive, right? That is contradiction to the statement here, which says that as long as f satisfies these two, then f of x naught must be equal to 0, right? That's a contradiction. That's where the contradiction is. Okay? A simple example of this is, suppose we just have some set of elements, and our f is taking 0 over this, over all the points. Okay. Now let's say we have another. So this is from the subset space of x, and also have another x naught is from x. Okay. Then we can claim that x naught is in the closure of the span, if and only if, let's according to the right hand side, says that f is in the x star, and f of naught over f m is equal to 0. That means f of x k is equal to 0 for every k in this m. This implies that f of x naught is equal to 0. Okay. A specific case is that m is just a bunch of points. Okay, but this actually holds for the whole, for this corollary where this m, it just needs to be some subset of x. Okay, that completes the proof.